This is Katie Bowman's AP problem number 6. So the problem, it says, after a 1 mole sample of HI is placed in an evacuated 1 liter container at 700 Kelvin, the reaction represented above occurs. The concentration of HI as a function of time is shown below. It gives us a graph that shows how it starts at 1 molarity, and then it goes down to 0.8, and then it gives us an equation 2HI yields H2 plus I2. So part A asks us write the expression for the equilibrium constant Kc for the reaction. So when you do Kc, it's products over reactants, and in the equation it gave us H2 and I2 were the products, and then HI was the reactants, and because HI had a coefficient of 2, that now turns into an exponent, so we get concentration I2 times H2 over HI squared. So then part B asks, what is HI equilibrium? And we figure this out by using the graph. And so it starts up here, and some people might think that 1 is actually the equilibrium, but because it's going down, that shows that it hasn't reached equilibrium until it gets right here at this line when it starts to flatten out, and then there's no change in this part of the reaction. So we know that right here, which is 0.8, that's where equilibrium begins for HI. So our equilibrium is 0.8 molarity for HI. So that's what I explained here. The graph shows that concentration HI equilibrium is reached at 0.8 molarity. So the next question, part C, asks determine the equilibrium concentrations of H2 and I2. So to find this, we use icebox. So our initial for HI is 1 molar, and then since there's no products yet, H2 and I2 are going to be at 0. And then here we have negative 2x. The 2 comes from the coefficient of HI, and it's negative because it's going to be losing its concentration. It's going to be going down. And then we have x and x, and they're positive because it's going to be gaining concentration. So we know that at equilibrium, since we learned that from part B, it's going to equal 0.8. So 1 minus 2x has to equal 0.8 to get the equilibrium for HI. So when we solve for x, we do 1 minus 2x equals 0.8, and then when we solve it all the way through, we get 0.1 for x. So we plug that back in right here for the equilibrium of H2 and I2, and since it's just x, we don't have to solve, and they're the same, so H2 and I2 equal 0.1 molar. So next, we move on to part D. On the graph above, make a sketch that shows how the concentration of H2 changes as a function of time. So this shows, so we know that H2 reaches equilibrium at 0.1, and the forward and reverse reaction reach equilibrium at the same time. So we know that at right here for time is where they're both going to reach equilibrium. It reaches it at 0.1. So we just have to get that graph going so that at 0.1 and on this line it reaches equilibrium, where the forward and the reverse reaction rate are the same. The concentrations don't have to be the same, but the reverse reaction rate have to be the same, so that it's losing and gaining at the same time. So next is E. Calculate the value of the following equilibrium constants at 700 Kelvin. So for this, we used Kc, which is products over reactants, and then we plugged it in. So we have 0.1 squared, which is H2 and I2 together. Since they're the same, you can square it. And then 0.8 squared, we just plugged in the equilibrium for HI, which is OH squared. That gives us 0.016. And then we use this equation to show the relationship between Kp and Kc. So Kp equals Kc times RT to the change in moles. So we're finding Kp. Our Kc, which we found up here, was 0.016. Our R is 0.0821 times 700 Kelvin. And then the moles is 0 because it's products minus reactants, and then there was 2 moles on the product side minus 2 moles on the reactant side. That gives us 0. Anything to the 0 was 1, which we see here. 0.016 times 1 is 0.016, so Kp and Kc are the same. That is because there's no change in temperature, and that's how it would become different. So we would just know that anyways, that there's no change in temperature. So really we didn't even have to solve, but it's always good to see exactly how that works. So moving on to F. At 1000 Kelvin, the value of C for the reaction is 2.6 times 10 to the negative 2 in an experiment, 0.75 moles of HI, 0.1 mole of H2, and 0.5 mole of I2 are placed in 1 liter container and allowed to reach equilibrium at 1000 Kelvin. Determine whether the equilibrium concentration of HI will be greater than, equal to, or less than the initial concentration of HI. Justify your answer. So for this, our concentrations are the same as the mole, because when you do moles divided by liters, which is just 1 liter, it's going to be the same. So we do products over reactants. So we have H2 times I2 over HI squared. We get 0.1 times 0.5 over 0.75 squared, which gives us 8.9 times 10 to the negative 2. That's supposed to say negative 2. It doesn't for some reason. And then Kc is, which they gave us Kc, is 2.6 times 10 to the negative 2. So when we look at these two and we compare them, Q is greater than C, so that means HI will be greater. It will increase compared to the initial. And that's it. Thanks for watching. Bye.